Okay, so thanks for the opportunity to Juan and to Diego. It's really been a pleasure so far. Okay, so I've been upgraded from the poster session, so I'm sorry for the people who already heard it in the poster session. So basically, imagine you have a circuit and you have two dipoles, I don't know, capacitors, and they can also do some, I don't know, Casimir business between them, exchange some virtual photons. I mean, is this such a, only a naive picture, or can we really start thinking about such things, So I'll let you judge, but this talk will be more about how to kind of start thinking about these things. So it's kind of the first step, and, let's see. So it's a more of a, methods kind of talk, and the results, I'm working on them now, basically. All right, so the beginning of this thing is you can start considering van der Waals interaction or Casimir nearby electromagnetic environments, like, confined environments, so people have discussed surfaces and stuff. So I will talk about waveguides. So let's say that in a waveguide, photons, they propagate in guided modes. So then, the van der Waals or Casimir interactions, they are mediated by these guided modes. So then you can have modified interactions. For example, these works have discussed metallic waveguides or the electric waveguides, and exponentially decaying interactions were found. For example, in here between two atoms embedded, two dipoles embedded in a waveguide. The thing that kind of, for me, began the story is to consider transmission lines. Transmission lines in general are at least two pieces of metal. So here it's just one piece of metal, but in a hollow form. But at least two pieces of metal. They are widely used in telegraph, coaxial lines, whatever you have in circuits. And what we found, which is quite intuitive, if you have this condition, so A is the separation between the metals, so this kind of the confinement, the transverse confinement of this creature. So if the distance between the interacting objects that are close, they are coupled to this waveguide, is larger than the separation, then you're still going to see 1D effects. So there are many, many, many transverse modes that mediate interaction, but the most dominant one is called the TM mode, and this mode really behaves like one dimension. So it's really a mode that goes like EIKZ and has no dispersion, namely linear dispersion. So then you can start talking about Casimir effects in one dimension, and just to show, the results that we were kind of excited about, and this is why I wanted to continue this work, is here, for example, we talk about the van der Waals interaction mediated by this TM mode, and we compare U is the interaction made by the TM, U free space is the one that I take from a textbook in free space, and you see that as a function of the separation, normalized to some resonant frequency of these dipoles, you have huge enhancement of the force because the scaling is logarithmic in short distances and small power law in long distances. So basically, the only thing you have to remember from here is that in this regime, where the TEM mode is important, which is very broad because this A, the separation can be microns or whatever, depending on your system, so you can really reach these distances where the dipoles are enough. And then you can start having these giant van der Waals, and you can start saying, okay, so van der Waals, at least for me, because I'm not from the quantum chemistry community, for me a dipole is the most elementary particle, and then van der Waals is the most elementary interaction I can have, so let's start playing. Now we have the basic one, we see it's giantly enhanced, so let's start doing other things. So let's do circuits of these transmission lines. So then the plan is one slide crash course on transmission lines, and then two ways to try to calculate Casimir forces or van der Waals forces between components in a circuit. And then, some conclusions on this thing. The first approach would be the straightforward one for people who come from Casimir, I guess. The second one will be just electrical engineering or first year physics, electric course. And that's it. Okay, so transmission lines. So we already said, we have these lines, these thick lines are not just the usual wires you have in a circuit. This is just representing these waveguides, okay? And then you also have these components. So let's start with the lines. It's these waveguides that we talked about, at least two pieces of metal. Then we have the impedance. It's just, the mu over the epsilon that we know from electrodynamics. But here, the epsilon is the capacitance. So each piece of metal or per delta x in this material, I have a capacitance and I have an inductance. So one is the mu, one is the epsilon, very simple. So this is what characterizes the transmission line. And then I can write the energy of each small piece. So I have a capacitance, so it's half capacitance per unit length v square, and I have inductance, so it's just the energy of an inductor, and this is per unit length, and that's the Hamiltonian. So if you like, this is half epsilon e square, and this is half mu h square, okay? So this is it. And then I can talk about my dipoles, or my matter. So this was my field, if you like. Now my matter. My matter is, let's start with non-dissipative matter. So it's a capacitor, inductor, or every other combination of these guys. So it's linear circuits for now. If it's non-linear, so I guess I would tell you that I'm doing like Woody. I'm saying that fluctuations are small, so I linearize. So if you want to put a transistor, go ahead. And then I can start thinking of, I put this guy in this transmission line. This transmission line is like my vacuum, my 1D vacuum of the world. And then I can have reflection coefficients and transmission coefficients of this guy is just a mirror. And these are the Fresnel coefficients. Actually, it's more general than in optics in a sense, because in optics you take mu to be mu0, and here it's really the real Fresnel coefficient, which is stated in impedances. Okay, but it's all normal incidence. So that's it. This is kind of the building blocks. And now the most kind of naive or straightforward adaptation of what we think of the Casimir effect would be to take two mirrors. So I take one component here, the other component here, and then there is this line between them, and also this infinity in both sides. So these lines are infinite, and I take the same impedance. So it's like I have refractive index 1, refractive index 1, refractive index 1, and in between, two mirrors. Okay, two surfaces. I don't know, graphene, whatever. Okay, so this is that's it. And then I can start asking. I know the Hamiltonian per unit length, so you can call it the stress tones, or I don't know, whatever. So it's just something very very easy. And then I can say, if I know the voltages and currents at the point, let's say I want to calculate the force on the mirror Z1, the impedance Z1. So I just if I know all the voltages and the currents at point x0 plus, then I know the energy here, and then I can subtract, and I get something like a force. Okay. Now, how to measure this force? Do they move? That's a different issue. We can discuss it later. But let's just start to understand the idea. So the only thing I have to find are voltages and currents given some noise sources. Okay. So now, which is like the quantum vacuum or whatever. So let's start with analyze it in the usual way. I mean, I'm coming from quantum optics, so the usual way for me. First of all, I look at the classical Maxwell equations. These are called the Telegraph Equations. So this is the curl E equation, this is the curl B equation, and then I get this 1D Helmholtz equation, and I get velocity, just the usual way. And I have waves propagating forward and backward, just 1D electrodynamics, the dream that we had before we knew how to before we knew what is the Attic-Green function. So this is the equations, and then I do the usual canonical quantization. I can write a lot. This is routinely done in the field of circuit QED. But these guys, they like to work with fluxes and charges, and I like voltages and currents, so I just redid it, and it's the same result, so everything is okay. So basically, I just take a Lagrangian that gives me this equation. I define canonical variables. I go to Hamiltonian, and here you go, we have a Hamiltonian. And then I can I identify the voltage. I can write it in a K space. Like in each K frequency, I have forward propagating, backward propagating, and of course Hermitian conjugate. And the voltage operator is just in analogy to the L here is quantization length. Okay, so it's infinity. It's not L capacitance. So this is the usual one. C prime replaces the epsilon 0 that you had in quantum optics or electrodynamics. Okay, so that's it. So we have quantized the free transmission line. So now we have our 1D free space. Okay, now we need to solve. Now what is the force? So we can write in terms of these. Again, we can write the density of the Hamiltonian, but in terms of this Vk. So it's very simple. It's the energy, V amplitude square. Of the propagating, forward propagating and backward propagating. Very simple, so that's the energy. And now I will have to, okay, so, and then, again, I need to find, let's say I want to find the force on the mirror number 1, it's the same like mirror number 2, by Newton's third law. So then I need to find the Hamiltonian at this point, so I need to find the voltages which I denote by the sub-index in the region C, the cavity region I call it. I also, so this is how I can get this guy, and I can get the other guy if I find the others. So basically, most of the information is here, basically, because this will have the length between the two guys, and I want to eventually get everything as a function of the length. And so I view this as the real thing that I need to find, and the other guy is just renormalization. And here it's very intuitive, because say it's really the force coming from the outside and opposing me. But really, when you think about it, it's just a renormalization. Okay, so now I have to find these voltages. Okay, so in the usual way, I know I need to find these voltages and these voltages to put them in this Hamiltonian density. So I need to find a scattering problem. So what is the scattering problem? I already quantized the voltage. So now I have noise that can come from infinity. So there is so this has been done actually. This 1D problem is I've been to 2 schools of Casimir physics, and Serge Reynaud, I've shown it always to motivate how we will derive in 3 dimensions the Lifshitz theory using scattering theory. And you always start with the 1D, and it seems like it's only a pedagogical game, but here it's actually useful. So I just got the same results that he got in 1991, not surprisingly. So not much has changed in 1D, whatever, scalar fields. So then you have the vacuum field coming from this guy, forward from minus infinity, and in the backward for plus infinity. Maybe, yeah, something like that. I did the opposite. And then the vacuum fields are just these guys that I said before. And we have, I assume that I have the vacuum or thermal, or whatever you want to put here, not squeezed state for now. And then I just have to solve this scattering problem. Such a fancy name in 1D takes like a few lines of calculation. And then I plug it in this H0 and I find something. You remember that I defined before these reflection and transmission coefficients for each impedance. And then I renormalize, I subtract the infinity, and here you go. This is the Lifshitz theory in 1 dimension, the Lifshitz formula in 1 dimension, if you like. And then you can do the V rotation, whatever, but let's keep it for some other time. Of course, I assumed here that these mirrors, they cannot eat energy. They're not resistors. They're just either capacitors or inductors. So this is simple, but maybe now it's more or less realistic. It's something that, because people have this circuit QD, they have these transmons, charge qubits, and but these guys wouldn't move. You're not going to measure a force in the most naive sense, so we were kind of thinking in my previous paper that I showed before that you should measure spectroscopy, like energy shifts, because of this van der Waals, similar to the talk that was here on the Casimir polder in front of the surface for atoms. Okay? Which in the quantum optics community, we usually talk about Rydberg blockades, huge shifts in the Rydberg atoms, but I mean, this is for other things. But, okay, so how to measure it, but we can discuss later on. Fine, so this is one thing. That was the scattering approach, QED. I feel embarrassed to say these words, just 1D, it's very easy, but still, you get the essence of everything. And most important thing, the noise source here was waves coming from infinity, the vacuum wave. So that's it. Fine. So now let's continue. But really this, let's come back. This thing, I just, there is a circuit. Okay? I can do many things with circuits. And I just, I forced the usual thing that we have all the time. I just do these mirrors. I didn't have to do this, right? I mean, why did I do just this? So I could do something a bit else. I could really, think of something else in a circuit, which is a resistor. And I guess you know where I'm heading. It's written there, like fluctuation dissipation. So by fluctuation dissipation, I know that the resistor, and now look, it's in open circuits. If the resistor was isolated, or only probed by a linear probe that doesn't really do anything, which is a voltmeter in this case, then it would have a current and voltage noise that I would know from the fluctuation dissipation theorem. But the question is, when I connect it to a different impedance, to a circuit, so can I just take the voltage from circuit QD and think that this is a voltage source and put it in the circuit? So this wouldn't really work, because I still want this resistor to be able to to respond to what's happening. So in my twisted mind, the way I thought about it is that I need to do something like a scattering theory. I need a source, and I don't want this source to disable this guy to respond. Okay? So the solution I came up with took me a lot of time. Is to consider this resistor, and then to put in parallel a current source. And this current source I will take from fluctuation dissipation theorem, and then I can connect these guys to the circuit. And then it doesn't matter that from the circuit maybe something will come here and there will be some voltage and current, but I will always be guaranteed to get the current from here. Now this is similar to the scattering formalism from before. The fields from infinity, they will come anyhow. Now something will happen there, but the fields from infinity will come. So that's the point, and that's the way I did it. And then because my office mate is an experimentalist in solid-state physics, I told him, when you want to calculate Johnson noise to see what happens in your circuits, what do you do? Do you do this? He told me yes. So I was like, oh, okay. So that's what they do. But the Johnson noise is not at zero temperature. This is Johnson noise is the opposite. It's the E beta H bar omega minus 1. Okay, but this is just a pedagogical note. So, and then I take the spectrum of this current from fluctuation dissipation, because I have resistivity of the resistor, and then that's it. I have everything. Now I take this and I can put it everywhere I want in the circuit and start analyzing fluctuation forces. You want to call it fluctuation, you want to call it Casimir, it doesn't matter. It's the same thing. Because for the circuit, it doesn't matter if it sees a resistor or the vacuum. It's the same thing. An atom, if it emits spontaneous emission to the vacuum or to some, I don't know, some phonon, because actually it's not an atom, it's a molecule, it doesn't matter. It's still the same decay rate. Okay? So the noise source here are really fluctuations from the resistor. Okay? So now, instead of taking this picture from before, I can replace these vacuums, these infinite transmission lines, with resistor. Now I'll tell you a story. All of the people who do circuit QD, when they tell you it's infinity, they put a resistor of 50 ohm. So actually this is how it's done anyway, experiments. But now I really have the noise. This, so this is the important thing. Now I can start analyzing. Again, it's the same story. I can write again the Hamiltonian density. And now again in spectrum. So this now I wrote it in spectrum instead of like propagate inward, forward and backward. I just wrote it in spectra in frequency space. I can still analyze the density of the Hamiltonian here because I will find the current and voltage here. Now to subtract this guy here, I mean, what is the meaning of the pressure coming from the resistor? It's not really understood. This is why I told you before, I really try to think of the other guy as the renormalization. It doesn't matter the interpretation that there is something from the outside. That's not the main point. And so now I just have to solve the current and the voltage at this point, and then I'll need to renormalize. That's the bottom line. And now the question is how to solve for the currents and the voltages. Before we had scattering theory. Do you have an idea how I solve it now? Any idea? So who has taken first year in physics and learned the Kirchhoff laws? So that's the nice thing. We just use the Kirchhoff laws now. That's the cute thing, you see? So, you do this current, they come and they're together, sum of currents, voltages, whatever, you find it. That's it. Okay? And now after you find the currents, you know the source current, so you can write the current and the voltage here as a function of these guys. Now, because it's all a linear system, if you have the spectrum from one guy, you can get the spectrum from the other guy. It's a linear system. So now I have the spectra of the voltage and current. I can put it into my Hamiltonian, this expression here. And here I get exactly the same result as before when I renormalize. But the meaning is different. Why? Because it was nice for me to solve the scattering problem when the impedances here were the same like the impedances in the cavity. It's like the refractive index was constant, only in the mirrors it wasn't there. It was different. If I would change it, I'll have a scattered wave also. I'll have some other problem, which is, I have to think how to match the K. And by the way, why did I didn't talk about reflection and transmission coefficients. So how come this formula is still written with reflection coefficients? Just because, you remember, they were defined by some impedances. So when I solved the Kirchhoff problem, I just got a bunch of impedances written here, and I thought, oh yeah, this guy, I remember it from the last slide, so then I wrote it and just get the same formula. Okay? So that's it. But the nice thing is now this resistor can be anything. It doesn't have to be the same impedance from here. And it's much more general because let's say that I have another resistor in the system. And I just take the association from the other resistor. It doesn't matter. Okay? So I can do, if my transmission line has a resistance, in quantum, in QED I couldn't quantize. Because I cannot quantize an open system, right? That's the point of the macroscopic QED. So it's more general. So now for some conclusions, which I actually already began here. So, my main message here, you all know it. It's just, another take, another kind of view on this. Some people, they like to view the Casimir force as they have a field and they have boundary conditions from the field. I'm saying forget about the field. There is no field. There is a system. And then the first step is I have to see which are the reservoirs of the system. Again, it's not new. It's just, I have to think about it. So who are the dissipators of the system? Then I use FDT. So each dissipator brings some noise to the system. And then I solve. You can solve scattering theory, you can solve a circuit, and that's it. And the vacuum, it's not nothing special. It's nothing special. It's just one of these dissipators. And if I had a cavity, a perfect cavity with perfect mirrors, but there was some, absorbing dust there, I would also have a Casimir effect. It would be just like the vacuum. Because again, when the atom spontaneously emits, it doesn't care if it emits to the vacuum, which is just the reason why the vacuum is a dissipator is because we have infinite boundary conditions. That's it. Absorbing boundary conditions. When I was an antenna engineer, we tried to understand how antennas propagate, and we were in a room. How can you do it? You put some absorbing boundary conditions on your wall. That's it. This is how people do it in simulation, right? So it's the same thing. So I don't say anything new here, but I mean, it's just another way to think about it. And then, just to test this idea, for example, I took a transmission line with a line impedance, which is R, and I tried to find what is the voltage noise that it inputs to some other transmission line. And I get some noise, and I did the same thing with a resistor with the current in parallel, and I get the same thing. Okay, so it's really the same thing. And then, let's summarize it. So we want to see if these circuits, they make sense, and first of all, I wanted to write like a formalism that is useful for this, and there are two formalisms. The one that we right away do because we are coming from quantum optics or whatever QED, and the other is the simple-minded one. And then the advantage that you solve what you learned and maybe you forgot. So it's a nice opportunity to remember how to solve Kirchhoff laws. I think for a circuit, it's a much more natural description anyway. You don't need to quantize. It's not that I don't like to quantize. It's just that when you have losses, if you want to quantize, you have to introduce these fictitious other fields, and then to trace them, well, what's the point? I mean, you just take the fluctuation dissipation theorem and go on. I mean, I'm not saying it's bad. I'm just saying, in here, for example, it's nice. And I can account for any resistance in the system, okay? So let's say I had some other resistor in the system, not the transmission, the infinite endless transmission line. I could do it with transmission line. I would do it for every resistor. I would put in parallel, I would replace it with another infinite transmission line, and another, and I'll have a circuit with many, many, many infinite transmission lines, and I will have to solve a scattering theory of all of these guys. I guess for some people it will be equally simple. But why? Why would you bother? So you just work with resistors, and that's it. And I think, for all of us, it's just because it's a very simple problem. It's also kind of pedagogically nice to see. Okay, we can think of, the scattering or FTT formalism that all of us kind of use in some way or another. To think of this analogy and maybe take advantage of it in other things. Now, the prospects for me. The prospects for me, and that's. Maybe, I'm already working on this and kind of advanced in trying to apply this formalism to observe some nice, forces or potential, or potentials between different components in the circuit or in the circuits, and to predict some nice things. The challenging thing that I'm working on now is to take numbers from experience to see which experiments, how, why, if it's at all realistic. Also, some divergences, for example, arise if you take a capacitor which is non-dispersive. Usually we take a capacitor, it doesn't depend on frequency. It's just like calculating the lamp shift and not taking the cutoff in the polarizability. So all sorts of stuff like that, one has to think of if you want to do a realistic prediction. The thing I'm most excited about, and what I found some exotic things like propulsion and stuff like that. But I mean, okay, first of all, I want to verify that it's really kind of true. So I don't show it here just because I'm not confident yet on these things. The other thing is, I think if this will work, then just like what Paolo has shown today, he showed an alternative way to measure Casimir forces, because it's just a different way, So this will be a different kind of force. It wouldn't be the usual one. It will be something else related to that. Maybe there will be advantages over the existing way, and there will be disadvantages, but at least there is an alternative way. So this is kind of my biggest hope here. But again, the devil is in the details, and this is the stage where I'm at now. But that's it.
Are there any questions? Yes, please, up there. Yes, yeah, up there, up there. No. You first. Okay, first Stefan, okay.
Okay. So if you want to take this literally, that it is a circuit, so what quantity would be the analog of the Casimir force? Or
what to measure?
Yeah.
So the most straightforward thing to say, which is like if we wouldn't want to think too hard, I would tell you let's assume that this part of the circuit is somehow has a spring constant, and this spring constant is moved. Then you'll gain two things in one. First of all, you'll have some capacitance which changes with distance or something like that. You'll have a parameter which changes, and also you'll be able to measure it. Another thing is what I said. If this guy is some flux qubit that you will assign, you'll find the response of this guy. Then you can measure maybe spectroscopy of this guy. This wouldn't be a force. It will be spectroscopy. The other thing is that there is something now which is optomechanics, right? So now there is optomechanics of circuit QED. So basically, you have circuit elements that move, and if they move, okay, you know what? Let's just take the usual Casimir experiment. If something moves, the capacitance changes. So here we go. You have a capacitor; it changes. So you don't even have to change distances now. You change other things, and that's the big thing. Okay? In my opinion.
Yes, please.
So if I understand your analogy right, so Z1 and Z2 are your plates, equivalent to sort of your Casimir plates.
Yeah, but they're infinitely thin plates, if you wish.
Yes. And the separation along your transmission line is basically equivalent to the separation between the plates.
Yes.
So, am I correct in saying that you could make the analogy that infinite impedance would be perfectly conducting plates?
Infinite impedance? Yes, because it's a reflection of -1. Yes.
So, but in the case of infinite impedance, doesn't your top and bottom transmission lines decouple? Because no current will flow through your...
My what?
The top transmission line and the bottom transmission line, there would be no... As there's no current flowing through...
This is why you have a reflection of -1, because if you cut them, it means that the current is 0. If the current is 0, it means that you have 0 boundary condition for the current wave. And this is exactly what gives it, like in a metal. What happens in a metal, in a perfect conductor, electric conductor? You have, for the transverse field, you have 0 boundary condition. This is why in order to satisfy this 0 boundary condition, you have to have reflection, which is the opposite in sign, but the same magnitude. No, it's the same. It's well known in transmission line theory. Okay, maybe it's like second year or third year electrical engineering. You know that reflection coefficients of all of these things. It's -1. For short circuit, it's a magnetic perfect material. By the way, I showed very easily that if I take open circuit and short circuit, it's just the perfect mu and the perfect epsilon. They repel. It's very easy. So it's the same idea, right? One of them is the perfect loop current, magnetic, and the other is the perfect capacitor.
Travel, please.
I was a bit confused. Yes, what's the difference between like what you presented and the derivation of Johnson-Nyquist noise using like fluctuation dissipation?
Right. I took it. We didn't even derive. I took it from them. No, I derived. Yeah, same thing.
Okay.
I just used it. There was a major. The only issue for me, I don't know, maybe somebody smarter would understand before that, is that there you get the current and the voltage on this guy when it's disconnected from the world.
But say you need like in Johnson-Nyquist you need like two. I mean, they are not disconnected from the world. Don't you need like one part of the circuit talking to the other? No.
What do you mean?
Yeah. Like you have maybe you go to the first line. I mean, you need two impedances, say, not necessarily resistors, no. Because, for example, if you have just one resistance, from where you get the noise.
So because the resistor has, these moving charges in it, because of temperature, this is the noise, current, the voltage you have.
It has to talk to another part of the circuit, right?
No, that's the point. I mean, the fluctuation dissipation theorem is written for, you take a slab of epsilon with epsilon prime, you have currents there. That's it. That's the one. It's the thing that is used in the software. I mean, if you had dissipation, so I guess this is what would be used in the software, right? I mean, you just put current from the system. So that's it. But this is if it's disconnected. Now, if you connect things, that was the tricky thing, how to do this. That's it.
Is there any other question? So I would like, because me to ask something, just curiosity. No, please, yeah. I have to ask something very important. Why do you consider this Norton instead of a Thevenin? If you were taking a Thevenin,
Maybe I could put, you say that I could take this one out and put a voltage source here and take the, maybe I just thought about this one, I tell you why, because I come from the optics, and in optics you put, yeah, but I tell you why I did it, because in optics you have a field equation for E, and the source is the polarization, which is a current. So this is my way of thinking.
Yes, Francisco?
Lindsay, you called me before I come with a question. This is what Mary was saying. It's just a precision. If you look at the paper of Nyquist, where he described the Johnson noise in 1928.
Which month?
Nyquist, 1928. You will find that it's not only at finite temperature. It's also with the Planck spectrum. So without doing the calculation, the quantum calculation, he extrapolates his result to the quantum world, and he got exactly this.
So he talks about you put a plus here and minus here and plus here. He talks about the S of minus omega. It's just
but what I mean is that it's not only finite temperature. It's also quantum. Nyquist calculated the fluctuations.
I know, but the Nyquist noise, which is the minus omega version of this guy, will be zero at zero temperature, regardless of quantum.
But these are the things.
No. This is okay. It's not our it's not only our KT, right? There is a quantum correction, but still at temperature zero, it's zero. That's it.
Any other question? Nothing? Okay, let's thank our speakers. At the end of this session, so Shahmoon